Multiplying functions. Let's start with an example. We're going to have two functions, f of x plus 2. So f of x equals x plus 2, that's the green function. And g of x minus 4, that's the red function. And what we're going to do is multiply those two functions graphically, meaning we're going to move along the graph and we're going to find some values and multiply them together. So they're a little bit off the graph at the moment, so maybe we'll start here. The y value on the green graph is 0. The y value on the red graph is -6. 0 times -6, we'd have a point right there. Let's see if I can draw you a very rough graph. So at -2, we're going to have an x-intercept. Okay, let's keep going. At -1, what are the two y values? 1 on the green graph, -5 on the red graph. So we have another point at -5. So at -1, -5. At 0, y value of 2, y value of -4. We'll have a new y value at -8. Let's keep going. At 1, we have a y value of 3 and -3. That gives us a y value of -9. At 2, we have a y value of 4 and -2. That's a y value of -8. So I think we found the bottom of the shape that we're going to end up with. We're just going to keep going up from here. Y value of 5 and y value of -1. So that's a y value of -5. And we'll do one more. Y value of 6, y value of 0. So there's another x-intercept. So it looks like the shape we're going to get is a parabola. Let's check. Yeah, there it is. I'm just going to zoom out a little bit so you can see it. And let me get rid of some things so it's not so complicated. Okay, so there's our nice new graph. Let's answer some questions. Equation of the new function. We took x plus 2, multiplied it by x minus 4. So x plus 2 times x minus 4 is the new function. Should make perfect sense. We have an x-intercept at -2 at 1 and 4. And there's our parabola. X-intercepts. Blue graph has an x-intercept at -2 and 4, which is exactly what we expected. Stationary points. This is so useful when you sketch the multiplication of functions. What points are on the blue graph that are also on the original? So we have these 2 points, the x-intercepts that were x-intercepts originally and remain x-intercepts now. Why is that? If you multiply y of 0 by any other value, you get 0. So if it was an x-intercept originally, it remains an x-intercept. There's 2 more stationary points. There's one here. Why did this point not move? I want you to look at the value on the green graph and see if we can figure out why that did not move. At this point on the green graph, I believe we were at 1. Let's see if I can get this back. Okay, lots of stuff happening here. Yep, there it is. And when you multiply 1 by anything, it doesn't change. So one of the stationary points comes from multiplying a y value of 1 by another value. We have another stationary point way over here. Why did that one not move? What do you think the y value is right there? 1. Okay, so when you have stationary points, either they're x-intercepts from original or one of the graphs pass through a y value of 1. And that is going to change everything when it's time to look for points on the graph. It's going to be so quick to get these points. Okay, let's keep going. What shape did you expect? We took a linear times a linear. So we took an x and multiplied it by another x. And when you multiply x by x, you're going to end up with x squared, which is a quadratic. So think about what happened if you multiplied x by x squared. You'd expect a cubic graph. Let's look at the domain. The original function, f of x, was the green one defined for all reals. The red one defined for all reals, so the blue one is defined for all reals. So again, for h of x to exist, it must exist in both g and f. Hard to get a new point when you can't multiply values together. So again, if this part of the graph did not exist, then the final graph would not exist there either. Okay, let's look at it. Draw a graph quickly. So you're given two graphs and you're going to multiply them, and let me just show you how fast this can be. Let's look for any x-intercepts. We've got one there, we've got one there, and we've got one there. So I'm looking for x-intercepts on either of the two original graphs. When you multiply a y value of 0 by anything, you get a y value of 0. So this point is on the new graph. Y value of 0 multiplied by anything, still 0. Y value of 0 multiplied by anything, still 0. So really quick to get those 3 points. Then we're going to look to see anywhere that our graphs pass at 1. Because anywhere the graphs pass at 1, we're going to end up with a stationary point. So we're going to end up with 3 stationary points. We'll see if we can find out where they are. So 1 times whatever value is there, that's where our new point is. 1 times whatever value is there, well, that was our x-intercept. 1 times whatever value is there, there's our new point. So the points that we're looking at, the point on the other function does not move because it got multiplied by 1. Okay, I'm just going to get rid of some lines so we can see what's happening. So I'm going to put them on again. X-intercepts remain x-intercepts. Anything multiplied by 1 stays where it is. So this is at 1, the other graph stays where it is. This is at 1, the other graph stays where it is. So those are 5 points found very quickly. Now we just need some more. -1 times 2 is -2. And what kind of shape are we expecting? This one is a quadratic of some form. This one is a linear. So we're expecting a cubic graph. Are we getting that kind of shape? Oh yeah, it looks like we are. So just another couple of points and we'll have enough information. -1 times 8, new point at -8. And maybe one more. 3 times 4 is 12. And that's how quick it is to do these. So again, look for your x-intercepts. They do not move. And then look for points where one of the graphs is equal to y is 1. So anywhere that one of the graphs is equal to 1, you'll have another stationary point and it'll be on the other graph. So you should be able to get through these fairly quickly. They're kind of fun. Today's exercise, 1 to 4. Enjoy yourself.